I'm Sheila CS. I recently submitted my PhD thesis. My PhD supervisor is Professor Joy Curie. I work in Network Research Lab, Department of Electronic Systems Engineering, Indian Institute of Science. First and foremost, I would like to thank Sitaram sir for giving me this opportunity. Today, I'll be talking about my work on intelligent cross-layer adaptation in IEEE 802.11ax double lens using Bayesian learning mechanisms. I try to keep mathematics part as simple as possible and try to convey the basic idea and important results. So we know that wireless communication suffers from many time-varying phenomena such as signal attenuation, channel fading due to multipath propagation, or interference caused by other users, etc. This leads to packet loss or bit errors whenever the link quality is poor. So in order to make efficient utilization of the channel, the transmitter has to select the appropriate MCS and then based on the current channel conditions, it has to adjust the rate dynamically. So this process is known as rate adaptation. Based on the method of assessing the channel conditions, the rate adaptation algorithms can be broadly classified into two categories. One is implicit feedback, the second is explicit feedback. In implicit feedback rate adaptation algorithm, the transmitter is going to assess the channel condition based on the transmission history, that is the success or failure of the previous transmissions. Basically, it depends upon the MAC layer acknowledgement frames only. When you go for explicit type feedback, here the receiver is going to estimate the channel and it sends the channel quality information, in short it is called as CQI, to the transmitter through the feedback channel. Implicit feedback type has some drawbacks, that is there is no real-time channel quality feedback available, and it has a slow response to the sudden change in the wireless channel, and it has no BR awareness. Also, this explicit type feedback has some notable challenges, that is modifies acknowledgement frames or it do some modification for the standard frame format structure. Therefore, it is not standard compliant. And it introduces additional overhead. Some of these algorithms, they introduce some new specially designed feedback frames, therefore introducing overhead. And there are also bandwidth utilization concerns. So as I told you, the current explicit feedback algorithms require custom feedback information and hence it's not standards compliant. So we sought to develop the standards compliant rate adaptation algorithms, prioritizing real world deployability and seamless integration into the current double LAN systems. So IEEE 802.11ax supports HE sounding protocol in order to facilitate the acquisition of the channel quality information. The access point initiates a secure request by transmitting a sounding trigger frame. The station responds with a HE CQI report via explicit feedback mechanism. So this CQI explicit feedback is supported by IEEE 802.11ax. So what does this HE CQI report actually contain? So it's an array of per RU average SNR values for each spatial stream, and each SNR value in this array, it is expressed in decibels, and it is arithmetic mean of the subcarriers within a 26 tone resource unit. So we have a granularity up to 26 tone, that is the minimum RU size, which is supported by 11ax. So before going to the proposed rate adaptation technique, I would like to touch upon this background topic called PHY-layer abstraction. So it's a technique used to simplify and accelerate the evaluation of wireless communication systems by approximating the behavior of the physical layer. So it's generally performed in advance, and the results obtained are stored to model the PHY behavior. So the state-of-art rate adaptation algorithms use this PHY-layer abstraction in order to estimate the success probabilities. So in our work, we employ received bit information rate based PLA, which is also recommended by Task Group AX through their reports. So this is a block diagram representation. Again, I'm not dwelling into the maths part of it. So we know OFDM is a multi-carrier communication system. When you say it's a multi-carrier, every subcarrier has some SNR, and we call it as SNR per subcarrier. So the basic principle of PLA is to map this array of subcarrier SNR into a single metric called SNR effective. So here in this RBR type PLA, what's happening is we have an array of subcarrier SNRs in the left-hand side. There is an RBR mapping function phi that takes this SNR per subcarrier and transforms the SNR into a information measure per subcarrier. So again, we have an array of information measure for every subcarrier. Then average information measure is computed. Then inverse mapping is applied in order to convert back this average information measure to a to the SNR domain. So this is the SNR effective. So now this SNR effective, whatever we have got through this function mapping, acts as a link between this AWGN PR and any frequency selective channel PR. So, but even this coding type, LDPC or BCC, and for given MCS. So basically, for OLBM system, using the single effective metric, which is obtained by PLA, we would be able to compute what is the instantaneous PR for given MCS. And we have validated the RBIR PHY-layer abstraction using the standard compliant double land toolbox. So here at every SNR point, if you see here, the x-axis represents the SNR in decibels and y-axis is the PR. At every SNR point, what we have done here is we have compared the PR obtained using the link level simulation, actual link level simulation, and the simulation setup is written over there, with the PR estimates which is obtained using the RBIR PLA. And you see there is a perfect, overall put agreement with the actual link level simulation curves and the PR estimated using the PLAs. So basically, this will be stored as a lookup table. So if you consider here, this is simulated for 20 megahertz. 11ax supports MCS 0 to 9. There are 10 MCS. So for every curve, you have this plot, right? SNR versus BR. It is stored as a lookup table. So because it is 20 mega, we have 10 such lookup tables. When I tell if you give me a point, SNR point, and given me a target PR, I can tell which is the best possible or the optimal MCS I can use it. Okay, this is the basic technique which is generally used by rate adaptation algorithms, and I think in LTE it uses EESM, exponential SNR mapping, and for Wi-Fi, RBIR PLA is good enough. So this is the schematic of the transmitter and receiver we have used in end-to-end link level simulation. We have used standard compliant double land toolbox to generate the standard compliant PHY-layer waveforms, 11ax OFDMA waveform. And we pass this waveform through a 11ax channel. That is again IEEE defined channel model. And in our simulation, I have used channel model D, which is typical office enterprise. And AWGN is added. And again, at the receiver end, we do OFDMA receiver processing, a packet detection followed by channel estimation using LLTF. Then HEC decoding, HECB in order to extract the transmission parameters like what is the MCS, what is the RU being allocated, what is the RU size for every user. So this is all being taken care. And also we do channel estimation using HELTF. And this is the packet processing, the signal processing, which is being used in all the proposed as well as the benchmark algorithms. One more point to note is we have done realistic least square channel estimation and frequency synchronization over frequency selective channel instead of oversimplified ideal channel and perfect synchronization assumption. Coming to the system model, I consider packetized data transmission over 11ax link. At every transmission instant, the wireless transmitter selects an MCS M of T. And the simulation tool is I have told. And we have modeled HU MU downlink transmission over TGX indoor relay fading channel with AWGN. So the channel estimation, as I told, we have used LLTF in order to estimate a channel at the beginning of the packet, and also used HELTF, that is a mid-envelope which is supported by 11ax, to estimate the channel when the packet is processing. So the problem statement is to design a Bayesian learning-based framework at the transmitter that utilizes a Bayesian update mechanisms to iteratively refine the channel SNR probability distribution with the objective of selecting the optimal MCS to maximize the expected throughput while maintaining the PR below a specified threshold. So here M is the set of the available MCS levels, and T of M represents the expected per packet throughput for a given MCS. RM is the data rate associated with that particular MCS. And here nu is the predicted SNR at the transmitter, which we get by sampling the posterior SNR PDF in a Bayesian learning framework. So more about this terms we'll get to know very soon. And PR is a predicted PR, and threshold we have chosen it as 10%. So now, because the packets are the entities which we transmit and receive, we wanted to know what is the SNR per packet or SNR per RU. So again, I'm not going to the math part of it. If the channel gains are exponentially distributed, then if the subcarriers SNRs are IID, we can be proved that the SNR over an RU, which is having ND number of subcarriers, as gamma distributed with that parameter. So gamma distribution has two parameters. So the first parameter is ND. This is the simulation settings or parameters. But the thing is, in 802.11ax, the subcarrier spacing is 78.125 kilohertz. They are closely spaced. It's very much lesser when compared to the coherence bandwidth, and hence subcarriers are not independent. Instead, they are correlated. So the correlation depends upon the various factors. Since the correlation structure is unknown, and also the fading is a composite type, what we did was we fit the observed histogram data, that is the SNR data, with the well-known PDFs, the model PDFs like gamma, normal, Rayleigh, Weibull, etc. And what we found was through this fitting that the SNR is fitting best with the gamma PDF. We have empirical evidence. And also in addition to this, we have some goodness of fit like KL divergence. I haven't added, but that is an additional test to check the goodness of fit. And also the literature indicates that for a Nakagami one channel or for Rayleigh fading, the SNR follows gamma PDF. So what is the Bayesian learning? We have used Bayesian learning technique in our algorithm. So it's a learning approach. So we continue to model SNR as SNR per area as a gamma distribution. So gamma basically has two parameters. First one is called the shape. Second is called the rate. So objective is to learn both the parameters, but the literature indicates that learning both the parameters is hard because the rate parameter has the conjugate prior has gamma distribution, but the shape parameter, it has no standard distribution which acts as a prior. So we kept the shape parameter fixed and continue to learn the rate parameter. So this is a prior distribution. D and E are the parameters. Because rate itself is a parameter and we are modeling that parameter as a gamma PDF, the parameters of the rate are called as hyperparameters. So here D and E are called as hyperparameters. So we use a standard hyperparameter update rule for gamma PDF where D hat and E hat can be updated based on the observations. So here nu k represents the SNR of kth packet, and n here is something to note. N is called the feedback window length. So to put it in simple terms, what is done here is for every n number of packets, the SNR which is observed at the receiver end is collected and is fed back. The sum is fed back to the transmitter. And this is a feedback. Using that feedback, the parameters are updated. Then you have updated parameters when you substitute to the gamma. It is called as posterior distribution. So now gamma D hat E hat is called the posterior distribution. So now from this you can find the posterior expectation. So the mean of this PDF would be simply the ratio of the hyperparameters D hat and E hat. So now you plug in that value to the original likelihood distribution. So you continue to do this. It's a like continuous process. For every n packets, you observe the SNR at the receiver end, feedback the sum, you go on updating the parameters. So this is the basic principle of Bayesian learning. So this illustrates the Bayesian learning based rate adaptation. So here it takes a standard compliant PHY-layer feedback, that is nu k SNR of kth packet. We use the original hyper update parameter rule. Basically, we model the SNR, the receiver SNR as a PDF probability density function. And based on the feedback given by the receiver, the hyperparameters gets updated, and we are trying the transmitter is learning the SNR PDF itself. And we predict the SNR by sampling the SNR PDF, and that is fed into the PHY-layer abstraction, which I discussed in the initial part. Then optimal MCS is selected. So in doing so, this is yellow bars represents the observed histogram at the receiver end, which is a ground truth. We call it as ground truth because this information is not available to the transmitter. The red line here indicates the PDF of the SNR, which is learned at the transmitter using Bayesian learning. And there's also perfect match in the CDF curve, indicating that the learning is good. So strategy, coming back to the strategy. So we know what is PLA, and at high level, I have told what is Bayesian learning. How it is being used in rate adaptation, I'm just covering this slide. So I told you we are going to update the parameter, that is a rate parameter, right, using the observed SNR at the receiver end, which is fed back to the transmitter. So now this updation happens and we take this likelihood distribution. I'm going to sample. So transmitter is going to predict the next packet SNR just by sampling this PDF. So that is the SNR predicted. Then this predicted SNR is fed into this PHY-layer abstraction in order to estimate the instantaneous SNR. Then I'll get to know what is the success probability. Using that lookup table, what I told you earlier, we will be able to, transmitter will be able to choose optimal MCS based on the target PR. So this is the results what we got. So here, the blue thing indicates the BLB, that's the Bayesian learning based rate adaptation. So x-axis here represents the feedback window length. If you remember, I told you n is something which is important because it is the number of packets after which the receiver sends the feedback. If n increases, the feedback overhead decreases, right? So we wanted to see the implication of increase in feedback window length or decrease in feedback overhead on the throughput. So Bayesian learning mechanism, if you see the throughput is consistent as we increase in the feedback window length, which is a desirable feature. But when you look at n equal to 10, there is a gap between the throughput of the other algorithm, HCDRA and BLBRA. So HCDRA is one algorithm. I don't go into the depth. The thing is, we proposed HCDRA first. There is no learning involved there. The objective function is the same. The MCS selection strategy is also same. But in HCDRA, there is no learning. But in BLBRA, learning of SNR of PDF is happening at the transmitter end. So in this, what we observed was there is a gap. So this raises a question, like why is there a gap, right? So next we focused on to fill this gap, like try to improvise the throughput. But in the consistency in the throughput with increase in feedback window length is something desirable. So we wanted to retain that. So that is what. So we wanted to, one thing is a desirable feature, but we wanted to see why not the throughput is, there is a gap at slower window length. Next thing we wanted to check was adaptability. So the key metrics in order to, the key metric to evaluate the rate adaptation algorithm is the convergence time to its optimal MCS. When I say convergence time, it is a time taken for the rate adaptation to choose optimal MCS whenever there is a sudden change in the wireless environment. Say the path loss changes, right? When a user moves from one place to the other, the path loss change, the receiver SNR change. So obviously you can transmitter cannot keep on transmitting the same MCS. It has to adapt quickly. So the question is how quickly it adapts. So that is the convergence time. So ideally, the convergence time has to be less. So here, say user moves from one point to the other, say close to AP, then the distance decreases and the SNR increases, right? So here, the yellow plots represents, so in order to emulate this real-time situation, what we did was, we simulated first 5K packets for transmitter distance is equal to 12 meters. Then the remaining packets processed were for 10 meters. So distance decreased. So the yellow bar is observed ground truth. So if you see the SNR range, it is less. When the distance decreases, path loss decreases, SNR improves, right? So the green histogram is that increased distance. Okay, this is a ground truth. It is not known to the it is not known to the transmitter. Whatever we have plotted, this is the measurement data which has been observed at the receiver and we have plotted, right? So next I'm going to show sample video where you will see the histogram, that is observation at the receiver end, and how the transmitter is able to track through the Bayesian learning the change in the SNR. Okay. Can you please play that video? Yeah. See, if you see here, the red curve is the learning thing which is happening at the transmitter end. The ground truth is changed. It is increased because distance is decreased. It takes some packets to track it. And after the number of packets processed increases, it is able to track. So the learning is happening at the transmitter end. So it is unaware of the change in the ground truth. Here, just for explanation sake of point, I have just overlapped the both. So the same thing here is explained. So it is after 5K packets, the green thing, the ground truth has changed. Learning is not happening. It is actually underestimating. After processing more packets, the transmitter is able to learn that there is a change in the SNR. And one point to note is he have fixed the value of alpha, and learning the rate parameter alone is sufficient to track the change in the spread of the underlying truth distribution. So our algorithm is efficient and is also lightweight. So same thing here, because the path loss was higher, the throughput was less. After initial few packets, the tracking was not happening. It was actually underestimating, because of which throughput was less. Later, it was able to pick. But the thing is, the convergence time here in this algorithm is 1940 milliseconds, which is around 2 seconds. And it's quite high for latency sensitive applications. So we wanted to decrease this convergence time. So next we proposed another algorithm, which is extended version of the previous algorithm. But I don't want to go into the details here. I'll just tell the core idea and show some important results. So this is a motivation, because we saw there is a lag in the throughput achievable for lower feedback window length. The question that arose was, can we improve the performance of BLBRA, the throughput performance, for small FBWL, while ensuring the desirable characteristic that the throughput remains almost constant irrespective of the feedback window length. So to address this, we retained the Bayesian learning framework, but now we change our objective and also the MCS selection strategy. So this is the block diagram representation. So earlier there was a feedback, there's a PHY-layer feedback. Now, instead of using the standard hyperparameters update rule, we have modified the rule. There is some standard rule for updating the parameters of the gamma PDF. So we have modified it in order to make it more adaptive. And in order to update that, we have made use of the MAC layer feedback in addition to the PHY-layer. So this is a hybrid scheme. It uses both PHY-layer feedback, which is available in the standard, and also uses MAC layer acknowledgement feedback. So this is the result we got. So actually, we have compared this algorithm with other two techniques, the reinforcement learning and map-based, but I don't want to go in depth to that because of the lack of time. So there is, again, we have this desirable feature where there is a constant throughput, and the throughput is also increased. So if you compare BLBRA with MET BLBRA, whatever the problem we faced earlier, now the throughput is increased. Again, checking the adaptability test. Earlier, we had two-step test. Here, what we did is we started with 15 meters, then decrease the distance, further decrease the distance. Again, came back, say, person moving from one point to the point A to point B to point C. Again, coming to point C and point E. So we wanted to see how quickly it can adapt in this situation. So here, if you see D equal to 15, because of the higher distance, path loss is higher, SNR spread is lower, x-axis is SNR, and D equal to 12, because of the decreased distance, the SNR is higher now. Again, D equal to 10, SNR is spread. So same thing can be observed now. Can you play that video? So it is tracking. Now the distance is decreased to 12 meters. So the red curve is the tracking which is happening at the transmitter end. So distance is further decreased. So the yellow bars are the ground truth which is observed at the receiver end. Again, the SNR decreased. So it is able to track. So within 3 to 4 feedback window, here the feedback window size is kept as 100 packets. So within 3 to 4 feedback window, it is able to track. And here the convergence time is reduced to 30 milliseconds. Again, here we have fixed the shape parameter. And hence, our algorithm is lightweight and it is able to track the ground truth. So to conclude, we have designed Bayesian learning based rate adaptation technique to decide the MCS to be used for the next packet by predicting the SNR at the transmitting end itself. So learning the rate parameter alone is sufficient to track the changes in the underlying truth distribution. We have modeled the end-to-end link channel using double-AND toolbox. And even in the presence of PHY-layer impairments, the algorithm is doing good. The proposed algorithms are eminently implementable using feedback mechanisms that are recommended by the standard. These are some references. Thank you. Any questions? Yes.
Yeah. So all these are done using MATLAB WLAN toolboxes.
Yes, yes.
So are there any alternatives, any Python packages on which we can do such PHY-layer Wi-Fi analysis?
Okay. I have not explored Python much, but double-AND toolbox I have been using. It has a very rich documentation actually. So once you use the standard like toolboxes and all, you need to study a lot. Python, I don't know much about it, but as far as my knowledge, this MATLAB double-AND toolbox is like you get to read. There is a lot of stuff available and you can implement it.
Thank you, ma'am.
Thanks.
Thank you very much. Yeah, I had one question about the predictive SNR thing that you are projecting. So SNR is it's a concept that changes periodically. How do you predict SNR? Because as the station or the client moves away from the API and comes again, so how do you do that prediction, and how successful it is in your experiments?
Yeah, that is what. If you remember in that block diagram of VLBRA, there is a feedback information which is fed from the receiver end. The thing is, when I tell the throughput was consistent even with the increased feedback window length, the algorithm is able to predict the SNR with decreased overhead. I am not telling that there is a feedback information that is observed SNR. The histograms and all what I have told, it's observed SNR at the receiver end. So the main idea here is, okay, receiver is estimating the channel, receiver knows SNR, it is very well known. Can the transmitter estimate? Can the transmitter predict at its end? That is the point. Yes, of course, for the transmitter to predict, receiver has to send feedback, right? So it will send the feedback. Based on the feedback information, I have modeled the SNR as a gamma PDF, and I'm trying to learn the rate. As you said, rightly said, when the environment changes, when the distance changes or whatever, the observation changes, right? Based on that, these parameters are going to change. Hyperparameters are going to change. So the SNR shift was happening. Whenever I change the distance, SNR, the range of SNR was either going to the right or to the left. That is a thing. That is a real time. I can tell it's an online learning thing which is happening.
And what is the periodicity of your SNR feedbacks? How do you measure it? Like, you measure it in milliseconds or nanoseconds, or what periodicity do you have?
Okay. Here I showed in terms of packets, it's actually in order of milliseconds.
Milliseconds.
Yes.
Thank you.
And in adaptability, if you say it is able to adapt quickly within 30 milliseconds, and I think that was about 300 to 400 packets.
Okay, thank you.
Thank you.